Hello and welcome to this Chemistry World webinar, Fingerprinting Recycled Thermoplastic Resins for Process Optimization. I'm Philip Broadworth, Chemistry World's Business Editor. For those of you not familiar with GoToWebinar, it's an interactive platform and you can ask questions from our speakers at any point, and that's one of the things where we think you get the most value about doing that. There's a box near the bottom of your GoToWebinar panel, which by the default is on the right-hand side of your screen for you to type in any questions you might have. If you miss any part of the presentation or you want to watch it again in your own time, we'll be sending a link to the recording next week, and we'll send a certificate of attendance in that same email. And today's webinar is about using thermal analysis and rheology to characterize polymers, especially recycled thermoplastic resins, which as we move to a more circular economy, is going to be a growing need for various suppliers and users of those materials. We've worked with TA Instruments to give you information that we think you'll be interested in from some real experts in the field. To make sure that everything runs smoothly, we've recorded today's presentations, but both of the speakers are here in the webinar and they'll be joining us for the live Q&A session at the end. They'll also be available to answer some of your questions in written form during the webinar. So if you want to ask questions, do get them in at any point. As soon as you think of them, type them in that questions box at the bottom of the GoToWebinar panel. Okay, so later on, we're going to hear from Terry Chen, who is a Principal Applications Engineer at TA Instruments, supporting rheology and dynamic mechanical analysis. But before that, we have Else Verdonk, who is a Senior Applications Scientist with TA Instruments, and she's going to be covering the thermal analysis side of the webinar. Okay, so I'll just ask my colleague Chris to launch the webinar, the video, and we will see you on the other side.
Hello and welcome to this webinar. My name is Else Verdonk and I will be covering the first part of this presentation. Let's take a look at plastic packaging, which is the #1 application for thermoplastic resins. There are a lot of advantages over other materials, including reducing food spoilage. But with a large volume of plastic that is being used worldwide, improper disposal has led to widespread plastics pollution, going from landfills to water bodies and affecting marine animals. Microplastics are also a concern, as the waste plastic breaks down in the environment into smaller and smaller pieces. Today, consumers apply pressure on brand owners to make their products more sustainable, and governments are setting targets for recycled content in plastics. This requires the plastic industry to innovate and develop new products. Every part of the value plastic chain needs to adapt. All of a sudden, the industry is moving from processing homogeneous virgin plastics to incorporating recycled content that can vary a lot from batch to batch. Therefore, proper fingerprinting and process optimization becomes increasingly important. In this webinar, we show you how thermal analysis and rheology can help you in this respect. In the first part, we'll discuss the use of DSC and TGA to check variations in the feedstock. But from these techniques, we can also get information about how to process the resin more efficiently. We'll show examples on recycled and virgin resins. Different types of thermoplastic polymers will be discussed: polyesters, polyolefins, polyamides. But of course, the outlined strategies will be applicable to other thermoplastics too. If you want more in-depth information, I would like to invite you to visit our website, where there is a dedicated section for polymer applications. Relevant application notes will be referred to in the presentation. You can download these application notes from our application library on the website. Now, as a first technique to fingerprint the materials, I would like to introduce differential scanning calorimetry. In the DSC, we are going to measure the heat absorbed or released by the sample while we are heating the sample or cooling it or keeping it isothermal. So we can get information about endothermic and exothermic phenomena taking place in your sample material. The DSC will provide us insight into the measurement of the glass transition of the material. Melting and crystallization temperature ranges can be studied. We can measure the crystallinity, or we can test the oxidative stability, the OIT or the OOT of a material. Fingerprinting the raw material using the DSC has quite some advantages. Small sample volumes are sufficient. A couple of milligrams, not more, is what you need. A wide range of samples can be tested, going from granules to powders or films or even liquids can be tested. And the testing time is very short, typically 20 up to 1 hour. Now there's a couple of special things associated with our DSC technology, like the patented T0 principle that gives you more sensitivity and resolution. Modulated DSC that allows separating overlapping heat flow effects, or the X3 DSC that is an instrument that allows us to measure 3 samples simultaneously, hence increasing your productivity. If you want more details about those special features, you can find them in these application notes on our website, or feel free to ask questions about it during the question session later on. Now, fingerprinting of the raw material with the DSC, I will make first of all an illustration of that by testing recycled PET that is intended to be used for the production of sandwich panels. Recycled PET from different sources can largely differ in molecular weight and impurities, and it's very important to get a feeling for that. So for that purpose, we will be studying recycled PET granules from 3 different sources. They are different with respect to their melt flow index. The viscosity is decreasing from sample 1 to sample 3. Typically, a lower viscosity is going to be related to a lower molecular weight. And we've measured those 3 samples in a DSC heating run after they have been ballistically cooled in the DSC. In a DSC thermogram, we will be looking at the heat flow measured as a function of temperature. And we will detect endothermic phenomena as downward phenomena. You can see here, first of all, at the lowest temperature, a step in the heat flow, and this is associated with the glass transition of the material. At a higher temperature, we see an endothermic peak that is associated with the melting of the crystalline phase. And occasionally, you can also see in between an exotherm that is related to cold crystallization of the amorphous phase. And especially when there's a lot of amorphous phase, cold crystallization will happen for the material. Now, the first conclusion that we can draw from the DSC heating runs on the 3 samples is that they are showing very clearly difference in behavior. We can also calculate the crystallinity from the heating run by measuring the enthalpy of fusion, taking into account the enthalpy of the cold crystallization, and ratioing this difference by the reference value for 100% crystalline PET. This is providing us with the crystallinity. And as we already had expected, the crystallinity is the lowest for the sample 1 because this one has the highest molecular weight. And longer chains have more difficulties to staple in a crystal lattice, so hence we expect a lower crystallinity. Based on molecular weight, we would expect a sample 3 to have the highest crystallinity. But this is not the case. It's the sample 2 that has the highest crystallinity. Most likely, this is due to more impurities in this sample that are going to act as nucleating agents. Now, DSC can also be used to qualify the contamination in recycled polymers if that contamination is of organic nature. Reason that we can make this qualification with DSC is that the different polymers have quite distinct glass transitions and melting temperatures. Here we are measuring a recycled polymer material, and we can clearly identify a melting peak around 133 degrees, which is telling us that this is a sample of high-density polyethylene. However, if we are zooming in on the high temperature region, we can see a very small melting peak around 164 degrees, which is telling us that there is some polypropylene contamination in the HDPE. DSC is also going to allow us to quantify the amount of contamination in a recycled polymer. In order to demonstrate that, we have put a known small amount of PET in LDPE, about 0.5 milligram of PET in a total sample of 14 milligram. This means that there's 3.6 mass% of PET in this sample. We can now quantify it by looking at the DSC run, and we will be looking at the second heating because we want to work with a material that has a known processing history. We measure here, first of all, the melting of the LDPE, but then at a higher temperature, we see here the melting of the very small amount of PET. By now ratioing the melting enthalpy to the melting enthalpy of a sample of pure PET that has been processed in the same way, we can now find that there's about 3.5 mass% of PET in this sample. So there's a very good agreement with the theoretical value in this mixture. Now, subtle differences in chain branching distribution or crystallizable chain length will have a large effect on the processability, but they cannot always be easily detected from ordinary heat-cool heat DSC testing. Here you see such an example where we are looking at 3 different polyethylene resins after cooling at 10 degrees per minute, and you can see that sample 1 shows a slightly different behavior than sample 2 and 3, but sample 2 and 3 cannot be discriminated. Solution can be here to make a differentiation by using longer stepwise isothermal crystallization profiles. Examples of such thermal fractionation techniques are SIST, stepwise isothermal segregation technique, or SSA, successive self-nucleation and annealing techniques. Both techniques are only showing minor differences, so I will only show an example here on the SIST technique. In this technique, we are going to heat a sample above its melting point, cool it quickly to room temperature, and then we will heat it to a temperature a little bit below the melting point to allow crystallization to take place, and we will keep it isothermal for a while. Then we decrease the temperature a little bit, keep isothermal again, so we will perform a stepwise isothermal crystallization for the sample. Finally, we cool it down, and we will take a look at how the melting is now showing up in a reheating experiment. And here you see that reheating experiment for the 3 different polyethylene resins after the SIST cooling. You can now see a lot of melting peaks instead of only one single. Every melting peak is associated with crystallization that takes place in one of the isothermal steps. And by now quantifying the ratio of the melting peaks with respect to each other, you can now clearly differentiate sample 1 from the others, but you can now also make a differentiation between sample 2 and sample 3. Now, DSC can also help us a lot in determining what is the processing temperature for the resin, because obviously the sample needs to be molten before you can process it, and DSC allows us to determine the melting temperature range. Here you see such a measurement for different type of polymers. And the onset of the melting region is clearly the minimum temperature at which we want to do the processing. And as expected, you can see that for low density polyethylene, this is already around 111 degrees, while for a sample like PET, you need to go to much higher temperature in order to fully melt it. In this respect, we will also going to use thermogravimetric analysis, TGA. In a TGA, we are going to measure weight changes as a function of temperature or time, and that will allow us to identify the start of the decomposition, quantify the amount of volatiles, or get an idea of the filler content in the thermoplastic resin. In a TGA, we have a highly sensitive balance to measure the mass of the sample. The sample is sitting in a furnace to control the temperature, and during the test, we are going to purge this furnace with an oxidative purge gas or an inert gas. If we want to, we can couple a spectrometer at the outlet to qualify the decomposition products or qualify the volatiles or the contaminants in the material. There's also some other specialties associated with TGA, like the high resolution option that allows better separation of overlapping decompositions for multi-component materials, or modulated TGA that allows us to obtain kinetic information. We have now measured different type of polymers with the TGA, and we will be looking at the weight changes as a function of temperature. And this allows us, of course, to determine the onset of the decomposition when the weight starts to drop dramatically. And that start of decomposition is obviously the maximum temperature at which we want to do the processing of the material. You can now see that there's not too much differences in those different polymers. The polyprop is the one that is decomposing at slightly lower temperature, a little bit below 400 degrees, while the LDPE is more stable. It only starts decomposing around 440 degrees. TGA also allows us to check the presence of volatiles and to measure the amount of volatiles in the material. As you can see here, the majority of the studied polymers are showing no or almost zero volatile release. But nylon 6 is showing quite a lot of volatile loss. There's about 2.3% of volatiles in this particular sample. This is important information to check if there will be off gases during or after processing. Whenever you're using TGA to study the decomposition of a material, you must be aware also that decomposition is a kinetic phenomenon. This means that it does not only depend upon temperature, but also on the time spent at a certain temperature. As a consequence, if you're going to heat the material faster, the onset of decomposition will be at higher temperature. You can see this in these runs where we took a sample of Teflon and we have been heating it at a heating rate as low as 1 degree per minute up to a heating rate as high as 20 degrees per minute. And you can see that if the heating rate is faster, the onset of decomposition is happening at higher temperature. One of the other consequences is that decomposition will happen even below the onset temperature if you keep the material isothermally for a longer period at that temperature. Now, this can cause a problem. If the melting temperature is close to the decomposition temperature, you will do the processing close to that decomposition temperature. So the question is then arising, how stable will your material be during the time that you need for proper processing? Solution to that is that we can run TGAs at multiple heating rates, or we can run a single modulated TGA experiment, and from that data we can get kinetic information like the activation energy for the decomposition. And once we have that activation energy, it can allow us to estimate the lifetime of the material as a function of the temperature at which we want to process the material. There's another application for this type of testing, and this is accelerated lifetime testing, meaning that short-term TGA experiments can also provide us information about the in-use lifetime at temperatures much lower than the decomposition temperature. Another important parameter that we need to study is the oxidative induction time of the material, the OIT. This will allow us also to evaluate the resin stability at high temperatures. This is a test that we will perform in the DSC, where we will heat the material to a temperature above its melting temperature. So you see here first during the heating, the melting of this polyolefin material. Then we keep the material isothermal at the temperature that we want to make the processing, for example, and we will switch the gas from inert gas to oxidative gas. And we will now start measuring from the moment that we do the switching, how long time it takes before the material starts oxidizing. And we can see that oxidation as an exothermic runaway of the heat flow signal. Now it's important that this time is long enough to allow us proper processing of the material. And if it's not, then we might need to add stabilizers to the material in order to make that OIT time longer. So this kind of testing gives us answer to questions like, can the resin be processed as it is, or does it need antioxidants? Which antioxidant is the most efficient? How much antioxidant is needed to process the batch? Also, OIT testing can give us some information about the end-use conditions and if the part has enough antioxidant for the final end use. When optimizing the processing, the cooling rate also has a big influence because it's going to affect the crystallinity of the material, and that crystallinity will impact important end-use properties like mechanical stiffness and strength. So what cooling rates are needed to achieve the required crystallinity? Instead of testing that on the processing equipment where we need to waste a large amount of material to do this kind of testing, we can much better do that on the DSC, where we only need a couple of milligrams of sample to get the desired information. Here I want to refer back to the recycled PET material that we studied earlier. We studied at that moment the crystallinity after ballistic cooling, and I've put it here, those values in a table. But we can also, in the DSC, process the material at slower cooling rates. For example, we can cool it at 10 degrees per minute and again measure in a heating run the crystallinity. You can now see that the crystallinity of the different samples is now very close. And also, as expected, crystallinity is much higher than crystallinity after ballistic cooling. Especially, you see a very big difference for the sample 1. Remember, this is the sample with the highest molecular weight. So for this sample, slower cooling has a very big advantage in comparison to fast cooling. For sample 2, the effect of the cooling rate is going to be negligibly small. Now, in reality, a high cooling speed is always desired because it allows you for shorter processing times, so will for sure give you some economical benefit. But that high cooling speed should not be at the expense of too low crystallinity, because too low crystallinity could lead to poor product performance. So we might want to add nucleating agents. These are additives that speed up the crystallization. We can very easily check their influence by doing DSC tests. So here is again the crystallinity for the PET material that was ballistically cooled in the DSC with no additives in it. If we are now adding additives to the material in order to speed up the processing, we can measure again the crystallinity after ballistic cooling. And we now see that especially for sample 1 and sample 3, this is very useful because the crystallinity has now increased a lot even after fast cooling. And we can also conclude that for sample 2, there was no need to add additives to it to speed up processing and still get a high crystallinity. Now, apart from the nucleating agents that are added on purpose to materials, there are other additives that will also influence the crystallization, like fillers, pigments, colorants, and you might want to check their influence too, of course. Well, with DSC, it's very easy to elucidate small differences by looking at a cooling run and study the crystallization. Here is an example where we study marker caps made out of polypropylene, and they have different colors, so different colorants are added to those samples. And when you look at the DSC cooling run, you can see that the crystallization exotherm is very clearly different. For the clear cap, crystallization is only starting at much lower temperature than, for example, for the purple cap. In order to get a better idea how to make the interpretation of these runs, we can make a partial integration of those peaks, and we can then plot the fraction crystallized as a function of temperature. The fraction crystallized being 0 at the start of the crystallization and being 1 when crystallization is fully finished. So we can now very clearly see that at a temperature of 120 degrees, for example, the purple cap is already fully crystallized almost, while the clear cap still needs to start crystallizing. If we make the graph in a slightly different way, and we now plot the fraction crystallized as a function of time, where time 0 is the moment that the crystallization starts, we can very easily get visual information about the rate of crystallization. And now we can see, for example, that despite the fact that the purple cap started to crystallize at the highest temperature, it does not show the highest rate in crystallization. It's the yellow cap that is going to show the highest rate of crystallization. So far, I have shown you a couple of examples of how DSC and TGA can help you to fingerprint and process your thermoplastic resins in an optimum way. And now my colleague Terry Chen will continue and discuss with you how rheology can help you in getting more information about this topic.
Hello everybody, I'm afraid we've had a little bit of a problem with Philip's microphone there, but what we'd like you to do right now while we get that sorted out is to answer the poll that's on screen in front of you. So as you can see, we would like to know which best describes your industry alignment with technology for sustainability. Is it mechanical recycling, so PCR content reformulating? Is it advanced recycling, pyrolysis and methanolysis? Is it bio-based polymers, redesigning polymers for end of recyclability? Or does this simply not apply to your area of research or organization? Now, hopefully you'll have all been able to hear me. I'm Ben Valser. I also work for Chemistry World, and I've been in the background helping to go through some of your excellent questions. Do please keep those questions coming in, and thank you for completing the poll. It looks like we should have Philip back online now, so I can leave you all to enjoy the rest of this excellent presentation. Thank you for your questions. Thank you for the poll. I'll hand back to Philip.
Okay, I think we're ready to close the poll now, Chris. So if you could show us the results quickly. It looks like a good mix of different industries. So I think, yeah, that's really useful to know, and that will really help us when it comes to the Q&A at the end in terms of framing some of the answers. Okay, so I think now it's just time to go on to Terry's video, and we can go straight through to that. Thanks very much, Chris.
Hello, everyone. My name is Terry Chen. I'm a principal application scientist at TA Instruments. In this following section, we will talk about how to use rheological technique to fingerprint polymer molecular architecture. Also, how to use rheology to guide recycled polymer processing. There are more related information which can be found from TA Instruments website. First of all, what is rheology? Simply by definition, rheology is the science of flow and deformation of matter. A rheometer is a powerful instrument that can measure the viscosity and viscoelasticity of a material. The measured material can be in a liquid, semi-solid, or in a solid form. The rheological measurement can provide important information about the material's viscoelasticity and viscosity information as a function of measurement time, temperature, and also under different shear conditions. Specifically, in terms of testing polymers, the rheological testing results can be used to fingerprint polymers' architecture, specifically molecular weight distribution, and launching branching structure. It provides a direct measurements to polymers' melt flow behavior, monitor melt stability, also through measuring the melt viscosity change as a function of composition or temperature, guide and help to optimize the processing conditions. The most commonly used rheological testing method for polymer melt analysis is under the dynamic oscillatory mode. In this type of test, the rheometer applies a sinusoidal strain to the sample and monitor the sample's response in stress. The shift between the input strain and output stress signals is defined as the sample's phase angle. From this oscillatory test, we can measure the viscoelasticity property of the material, which are described as modulus and complex viscosity. For polymer melt analysis, there is a specific ASTM standard, which is the ASTM D4440. This standard describes of using a dynamic frequency sweep test method for measuring polymer melts under their molten temperature. The testing results provide information on polymers' storage modulus, loss modulus, and complex viscosity changes as a function of testing frequency. For virgin polymer resins, this measurement results can be used to directly correlate to polymers' molecular weight and molecular weight distribution information. In most cases, the traditional flow viscosity measurement as a function of shear rate is limited for testing molten polymers. From this video, we can see that the polymer sample undergoes an edge fracture even before the shear rate reaches 1 reciprocal second. This edge fracture phenomena is caused due to the viscoelastic nature of the material. Therefore, most of the reported polymer melt viscosities in rheological measurements are actually obtained from a dynamic frequency sweep test, and then going through a Cox-Merz transformation. Cox-Merz is a practical rule which directly converts the dynamic complex viscosity measured as a function of frequency to the shear viscosity measured as a function of shear rate. Many researchers have proved that this Cox-Merz relationship works quite well with polymeric materials, especially for polymer melts and polymer solutions. Using this method, we can successfully extend the polymer viscosity information up to a higher shear rate, which correlates to the shear conditions in processing. So, what do we learn from these rheological measurement results? First of all, let's look at the viscosity signal. From this viscosity versus shear rate curve, we can see that polymer melts are shear thinning. Under low shear rates, the viscosity curve reached to a Newtonian plateau, which can be extrapolated to the zero shear. This measured zero shear viscosity is sensitive to polymer's molecular weight. When polymer has low molecular weight, its zero shear viscosity is linearly proportional to its molecular weight. Once the molecular weight exceeds a critical value, polymer chain starts to entangle, so molecular mobility decreases rapidly. From this point, any further increase in molecular weight shows a much faster increase in its viscosity. Therefore, we can see that the slope of this straight line increased to 3.4. In certain cases, this value can be even higher. Sometimes it can be as high as 3.5 or even 3.6. From this relationship, we can see that simply through comparing the zero shear viscosity, we can compare the differences of molecular weight between different batches of polymers. The higher the zero shear viscosity, the higher the molecular weight. In addition to compare molecular weight, the shape of the viscosity versus shear rate curve can also be used to compare the differences in molecular weight distribution. Polymers with wider molecular weight distribution always shows an earlier shear thinning compared to the polymers which has narrow molecular weight distribution. Because those low molecular weight fractions in polymer help to increase the molecular mobility, which causes the polymer to shear thin at the earlier and lower shear rate. Here is one good case study results of comparing the molecular weight of 4 recycled PET resins from different sources. Even though these feedstocks may contain small amount of unknown impurities, it is still reasonable to use this rheological method to compare the differences in their molecular weight. From this figure on the right here, we can clearly see that the viscosity of sample 1 is high and is close to the viscosity of virgin PET. But for sample 2, sample 3, and sample 4, they have significantly reduced molecular weight due to feedstock processing, such as grinding. Also, just compare this sample 3 and sample 4. They both have similar zero shear viscosity, which means they may have similar molecular weight. But sample 4 shows more shear thinning behavior, which indicates that this batch feedstock may have broader molecular weight distribution. In addition to just use the viscosity signal, in frequency sweep measurements, the shape of the G' and G" curve and also the G crossover point are also sensitive to polymers' molecular architecture. Polymers are inherently viscoelastic. Under higher testing frequencies, which correlates to short timescales, the polymer chain relaxation may not be able to fully following the testing frequency. Therefore, it behaves more solid-like, with G' greater than G double prime. While at lower testing frequencies, which correlates to long time scales, the polymer chains are able to fully relax over the duration of deformation. So it behaves more viscous with G double prime greater than G prime. Within this testing frequency range, this G' G double prime crossover point is sensitive to the molecular relaxation. This is commonly used as a sensitive indicator to compare the differences of polymers' molecular weight and molecular weight distribution. First of all, this G crossover frequency is sensitive to compare the differences of molecular weight. When testing different batches of polymers, if one batch shows the G crossover point at a higher testing frequency, it means that this batch may have relatively lower molecular weight. Second, this G crossover modulus is sensitive to compare the differences in molecular weight distribution. If one batch of polymer shows the G crossover modulus occurred at a much lower modulus, it means that this particular batch may have a broader molecular weight distribution. For some common polymers, such as polyolefins or polystyrene, TA Instruments Trail software can directly use the rheological testing data to calculate the absolute molecular weight and molecular weight distribution. And we have proved that the calculating results correlates quite well with the GPC and SEC testing method. Here is just one example of using TA Trail software to calculate the molecular weight and molecular weight distribution of a virgin polypropylene resin. Many of the processing flows, such as blow molding, are elongational flows. This type of processing is very sensitive to polymer chain entanglement, which is related with polymer long chain branching structure. So in this case, a nonlinear elongational test is more sensitive in probing polymer chain entanglement compared to the traditional dynamic frequency sweep. There are different models of extensional testing accessories on the market, such as the SER, EVF, or EVA. All of them are capable of measuring the extensional viscosity of molten polymers at different extensional rates. When testing the extensional viscosity of a linear polymer, in here we're testing a linear low-density polyethylene sample. Its extensional viscosity tested at different elongational weight, the rate looks like this. In value, the steady-state elongational viscosity equals to 3 times of polymer's zero shear viscosity. When testing a polymer that has long chain branching structure, in here we're testing the highly branched LDPE polymer, its extensional viscosity curve shows this kind of strain hardening effect. And the higher the elongational rate, the earlier the strain hardening starts. Therefore, the extensional viscosity of a branched polymer is greater than 3 times of the zero shear viscosity. From these test results, rheologists have defined a new parameter, which is called the Troughton ratio. Troughton ratio is the ratio of the extensional viscosity to the zero shear viscosity. So nowadays, people have been using this Troughton ratio to quantify or to compare the degree of long chain branching in polymer resins. In polymer processing, melt viscosity is always the key parameter to processing engineers. For example, people always ask the question such as, is the viscosity of this resin suitable for extrusion? Many of the polymer manufacturers only provide to their users with a simple melt flow index value to correlate with their resin's melt flow property. This single point evaluation is proved to be not sufficient. As we have talked earlier, polymer melts are shear thinning. Its viscosity decreases with increasing shear rates. So two resins may have the same melt flow index, but they can exhibit significant differences in their flow behavior under different processing shear rate. This figure here outlines the shear rate range required at different types of processing. For example, in a single screw or twin screw extrusion, the polymers are under a shear rate from tens to a few hundreds of reciprocal seconds. But in an injection molding process, the required shear rate is much higher. Using general rheological testing, which is the frequency sweep test, we can measure the melt viscosity of a polymer up to a little over 628 reciprocal second shear rate, which is the highest frequency a rotational rheometer can achieve. The higher shear viscosity information will need to be obtained using a capillary viscometer or through this time-temperature superposition technique. Here is one case study of evaluating the melt viscosity of recycled polypropylene resins, which containing different amount of impurities and fillers. The direct rheological measurement provides the melt viscosity information at the extrusion shear rates. And also, with the combination of using the TGA analysis, we can get a better understanding on their flow behavior. The reason why sample 1 shows higher melt viscosity compared to the other two samples is because this particular resin containing about 25% of the inorganic filler. This is another case study of comparing the melt flow behavior of regrind fiber-reinforced recycled PBT resin to their virgin resin. The results have clearly showed that the regrinding process largely affects their melt flow viscosity. Grinding causes partial polymer degradation and also damage the glass fiber reinforcements. So this testing results show that the 100% regrind resin has significantly reduced melt viscosity. Using this rheological evaluation, we can provide information on how much regrind reduces melt viscosity. And also, we can guide the processing engineers on how much virgin resin that needs to be mixed with the regrind in order to achieve the ideal melt viscosity for processing need. Another question people always like to ask in recycled polymer processing is the resin stable at the processing temperature? Different analytical techniques will provide the answer from different perspectives. As Alice has discussed earlier, the TGA analysis can help to determine the start of resin decomposition temperature. The DSC technique evaluates resin's oxidative stability at processing temperatures through this OIT and OOT method. Well, using rheology here, we will be directly monitoring the changes of melt viscosity over the time of processing. Here are some examples showing how to use rheology to monitor processing stability. We load the sample to the rheometer and conduct a dynamic time sweep test at the target processing temperature. If the polymer is stable, its melt viscosity should remain constant over time. But as we look at these two examples here, for processing polypropylene at temperature of 230 degrees C, we see that its viscosity decreases over time, which indicating that this polymer undergoes a molecular weight reduction. Well, in the case of processing PET at temperature of 280 degrees C, we observed that the PET resin, the viscosity increase over time. This means PET undergoes a slow cross-linking at this processing temperature. If this resin is not properly dried, this increase in viscosity can be even faster because small amount of water in this resin can accelerate this cross-linking reaction. So in both of these cases, considering properly lower the processing temperature could potentially keep the resin more stable. Then the next question comes up. What will be the optimum processing temperature? If the processing temperature is too low, the sample will not be fully molten. And even if it is molten, its melt viscosity could be too high to extrude. But on the other end, if the processing temperature is too high, then sample will not be stable, or the melt viscosity gets too low and inappropriate to achieve a good mixing. Using the combination of thermal and rheological characterizations, we can help the processing engineers to address this question. As Alice has discussed earlier, the DSC technique can measure the crystal melt in the resin. This end of melting temperature can be considered as the lowest processable temperature because at this point, the sample is fully molten. Actually, in the real world of extrusion process, the shearing on the polymer chain causes some early melting on the crystal structure. So that being said, this end of melting temperature can be used as a reasonable starting point. Here, we're showing an example of 3 recycled PET resins. From the DSC study, we can see that their end of meltings are showing at the temperature of 255 to 260. So the next question is, then what are these resins melt viscosity looks like at this particular temperature? To address this question, we then load these 3 samples to a rheometer and then conduct a dynamic temperature ramp experiment. From the end of melting temperature, and here we start from 260 degrees C up to 280 degrees C. From these test results, we can quantitatively monitor the polymer resin's viscosity change as a function of temperature. Particularly talking about the case of these 3 resins, we can see that sample 1 has higher melt viscosity, especially under lower temperatures. So this means, particularly for this batch, it may require a higher processing temperature. But the viscosity of sample 2 and sample 3 are all low. They can certainly be considered to process at a much lower temperature. We then summarize the viscosities at different temperatures into this table. This table provides a good guidance to the processing engineers on what will be the optimum processing temperatures on different batches of PET resin. Since the viscosity of resin number 3 is too low, it may even need to consider to mix this resin with certain percentage of virgin PET in order to achieve an ideal melt viscosity. Here is a summary of most of the key polymer processing questions that can be answered using TA Instruments analytical techniques. First, the DSC can help to measure the crystallinity and crystal melt of feedstocks. DSC can monitor sample oxidative stability and also help to guide processing temperature. TGA determines the resin's decomposition temperature. It can quantitatively measure the amount of impurities and fillers in different batches of feedstock, while the rheometer can fingerprint the polymer's molecular architecture, monitor polymer melt flow behavior, and also help to guide polymer processing. Both thermal and rheological techniques are important and can be used in product innovation, troubleshooting, and also processing optimization. With that, I would like to end today's presentation. Thank you very much for your attention, and we are very happy to answer your questions.
Brilliant. Okay, well, that's the end of the videos. So I'd like to invite Else and Terry to turn on their cameras and join us for the live Q&A part of the webinar. And hopefully everyone can hear me this time and I haven't muted my microphone. Terry, I can see you, and Else, you've both got cameras on. Can you just check that we can hear you both as well?
Hi, everyone.
Yes, I have unmuted myself. You should now hear me.
Excellent. Right. Okay, so we've got some really great quality questions coming through from the audience. So I'm going to crack straight on with those. And the first one comes from Steve, and it's for Terry. And it says, in addition to detecting cross-contamination with different types of polymer, can you use these techniques to determine the levels of other residual contamination, for example, the contents of what was in a plastic packaging before it was recycled?
I think this is a question for me too. Shall I start, Terry?
Yes, please.
Well, there's two different ways in which you can easily detect other residual contamination. First of all, if the contamination is decomposing at a certain temperature, and it's decomposing at a temperature that is slightly different from the temperature where your main polymer is decomposing, then you could quantify with the TGA the amount of contamination. And if you then couple your TGA to a mass spectrometer or an infrared spectrometer, you can then additionally with the spectrometer qualify what are the decomposition products that are being released and try to find from those decomposition products what is the native contamination. Or in case that your material, your contamination is showing a heat flow effect, can be a melting point or a phase transition or whatever heat flow effect it's going to show, then you can measure it with the DSC up to 700 degrees typically. But if your contamination would show some heat flow effect at higher temperature, with a combined DSC TGA, you could even go to 1500 to try and detect it.
Great. I think that answers that really nicely. And just as a sort of extension question from Casey, for the contamination analysis, which I think is more referring to other polymers, can you give an idea of what the rough detection limits are for contamination?
Yes. The rough detection limits are really going to be dependent a bit on what type of contamination it exactly is. If we are looking, for example, at the DSC, and the contamination is something that shows a melting peak, and it's a metal, a small amount of metal particles, well, metals have very sharp melting peaks and are therefore very, very easy to detect in a DSC. So a couple of milligram of melt of a metal, a couple of micrograms, sorry, of a metal, you will already capable to see the melting peak in the DSC. If it's more about polymers, then it will depend a bit on what transitions are in the polymer. If the polymer shows a melting peak, typically in the order of a couple of 100 joules per gram, well, at that moment, polymer melting is rather broad, so the peak will be a bit more smeared out than the metal melt. So that means that you will probably roughly need around 100 microgram or even a bit less, and you can detect it. If it's an amorphous polymer that is only showing a glass transition is a weaker transition than a melting. At that moment, you might need a bit more, but for sure a couple of 100 micrograms should typically be good. And you can always play with the heating rate that you are going to use in the DSC. At the higher heating rates, you get more sensitivity. Or you can also play with the sample mass. And if the amount of contamination is very small, put a bit more sample in your DSC cup to also increase the sensitivity.
Great, thanks very much. Okay, so the next question I think is probably more for Terry. So you had a slide about switching to oxidative heating on the DSC, and it says you can use air or oxygen. Does that mean you actually have to connect the DSC up to a pure oxygen supply, or does it just use air as the carrier for the oxygen?
This is the L's question.
Yes,
Is
I
it?
will also.
Hang on.
I will
No,
also take this one.
sorry.
You have the choice. You have the choice. You can either connect air to your DSC, or you can connect pure oxygen to your DSC. Everything depends on which ASTM norm you are going to follow. So you can just follow what the ASTM norm is dictating you. And all of the DSCs do include a switching device. So that means you have two gas inlets, one for nitrogen, which is a typical purge gas that you will be using, and a second one on which you can couple air or oxygen. And you can then in the software in your method program that at some point there should be a switching from nitrogen to air or oxygen.
Okay, thanks very much. And I apologize for directing the questions in the wrong way. I've been having some technical problems in the background, so I haven't necessarily been able to exactly follow on which bits of which presentation the questions are coming in relative to. This definitely is a question for Terry now. So when we're recycling polymers, sometimes different polymers are not necessarily compatible with each other. And how can you give some idea of how you can process those together, or can you measure the mechanical properties when they're mixed?
This is a great question. Actually, to investigate a small amount of residue impurities is not, rheology is not that sensitive to do that. That actually belongs to using thermal technique, like what Els just mentioned about using DSC and TGA. But for talking about polymers, which containing a lot of, it's a polymer blend system. Yes, rheology, well, more specifically, we'll say actually a dynamic mechanical technique is actually the way to differentiate whether or not we have incompatible polymer blend in this recycled system. So specifically, we can conduct a dynamic temperature ramp experiment to determine this the compatibility of these two polymers, and as well as using rheological measurement in combination with something like SEC imaging, microscope, you can actually see the compatibility. In lots of industries, in order to to get this incompatible polymers to be more mixable. So they're trying to consider using some compatibilizer, which are some diblock or multi-block polymers to enhance the compatibility in order to, to improve the mechanical properties of their end use product. Because of the time limitation, in this talk on the rheology section, I only focus on melt rheology processing and did not get any chance to talk about the end product, mechanical strengths. If the polymers is like the recycled polymer is a mix of immiscible polymers, the final end product property will be significantly affected.
Great, thanks very much. And maybe as a sort of follow on to that, if we're talking about blended feedstocks from recycling, can the thermal or rheology techniques give you a kind of quantitative measure of the amounts of different polymers in those mixtures?
From the rheology side, we may be able to see that we have certain different amount of different polymers in this feedstock, which using the frequency sweep and then testing the data down to really, really low frequency, you will see the shape of the G prime, G double prime curve will look different. But from the DSC technique, Els can explain that you are able to see if the polymer is a semi-crystalline polymer, you should be able to see they melt at different temperatures. You should see different melting temperature. So Els, maybe you can add more answers to this question.
Yes, if the polymers do not mutually influence each other, you will then see indeed different melting temperatures. And if you then also measure the pure polymers and know the melting enthalpy for the pure polymers, by simply making the ratio, you can then quantify how much of which polymer is in that blend. Yes.
Great, thanks very much. That's a really nice answer to that question. Okay, so I think we're going to go for the last question now. We've had a few people asking about sort of crystallization and heating or cooling rates. So Mike has asked, and this is probably, I guess, for Els, with faster cooling, you get crystallization or you see crystallization at a slightly different temperature. Is there a quantitative relationship between the cooling rate and the crystallization peak temperature?
Yeah, Mike, you are probably referring to crystallization kinetics. Now, quite often when people want to study crystallization kinetics, they will not do that by doing cooling at different rates, but they will make isothermal experiments and check at different temperatures how long it takes before the material starts crystallizing. And you can then fit your DSC data to different models. There's, for example, the ASTM norm D2070. And in that norm, it's described to fit a special form of the Arrhenius equation to the time where the crystallization peak reaches a maximum. And out of that fitting, some kinetic parameters might then be obtained. But more often, people will use a more complex method, and instead of only looking at the peak maximum of the crystallization, they will look at the full exotherm of the crystallization and make partial area integrations to get information about how much material is crystallized after a certain time. And then they will fit the full information to different kind of models. One example is the Shestak-Berggren model, but people also are using Malkin model or Avrami model. Now, the way how to do that is that if you're good in Excel, you could program this by yourself because it's very easy to export our data to Excel and then do your own thing in it. But if you don't like to do this by yourself, we have a special option in the trios for which you need to have a kinetic key. That is a separate option in the software. And then the software will make that a fitting with the different models for you.
Great. Okay, and The flip side of that question, I guess, was relating to heating rates for looking at melting. And we had two questions, one from Bettina, which was, is it sensible to do these kind of TGA measurements at the temperature that you're anticipating to process the polymer rather than doing a ramp? Or as a related question, how do you kind of work out what the best heating profile might be?
Yeah. So Bettina, what you are referring to is also fitting some kinetic models to your TGA data, so you can study the decomposition at different heating rates. And obviously, you are going to see that if you are working at different heating rates, the decomposition will shift to higher temperature with higher heating rate, and from that you can obtain kinetic information. And once you have that kinetic information, you can then make a prediction of how long it would take for your sample to start decomposing at a certain temperature. Now, the processing, if you do that at a temperature very close to start of decomposition, then the decomposition will go very fast. And then you could indeed make your life more easy. And instead of doing that kinetics, you could just make a measurement where you keep your material for some time isothermally in the TGA and watch how long it takes before it starts degrading. And this is then only one single test. But quite often, people want to know how long it takes before decomposition starts at temperatures much lower than where you see start of decomposition in the TGA, especially for lifetime prediction, not necessarily for processing, but more for the final product, what will be the lifetime of that. And then making this isothermal test in a TGA would take tremendous amount of time, so people will not do that. And at that moment, they will be using those kinetic models to fit to their TGA data.
Brilliant. I think that's answered some really great questions there, and you've given some really fantastic answers and highly detailed. So thank you very much, both Terry and Els, once again. I think that's all we've got time for. But if we didn't get around to your questions, then all of them will go to Terry and Els, and they may be able to get back to you offline at a later date. So thanks again to all of you for submitting those questions. That's what really, I think, makes these sessions as valuable as possible for everyone to really get into some of that detail with these real experts in the field. Thank you all for attending, and just to remind you, you will get a link to a full recording of this session next week, and with that will be a certificate of attendance. And if you did like this webinar and you want to look at what we've got coming up in the rest of the Chemistry World series, we've got some more scheduled in the next few months. Do check out chemistryworld.com/webinars to see what's coming up. And I hope to see you in another Chemistry World webinar soon. My name is Philip Broadrith, and I am the business editor of Chemistry World. Thanks very much.